good morning. Our group is going to be discussing about advanced gas cooled reactor or MAGNOX reactor. So in our report, we're going to be discussing about the introduction, the basic concept and theories, the operation concepts such as the plant arrangement and safety criteria, and the designs of systems such as mechanical design, nuclear design, and fuel assemblies, to name a few. So for our introduction, advanced gas cooled reactor or AGR is a type of nuclear reactor which uses graphite as a neutral moderator and carbon dioxide as a coolant. One specific example is a MAGNOX reactor. However, newer generations allow for it to operate at higher gas temperatures for improved thermal efficiency. Although the advanced gas cooled reactor requires stainless steel fuel cladding so that it may be able to withstand a higher temperature. Since stainless steel fuel print cladding is used, stainless steel fuel cladding has a higher neutron capture cross section than MAGNOX fuel cans. Enriched uranium fuel is needed, and all existing first prototype advanced gas cooled reactors have become operational in 1962. But the first commercial AGR did not come online until 1976. Now, for the concept and theories, in AGR, components such as the reactor core, boiler, and gas circulators are enclosed in a single cavity, which is usually made of pre-stressed concrete pressure vessel. Moderators are made of 16-sided stack of graphite bricks, designed in a way to provide individual channels for fuel assemblies, control devices, and coolant flow, as seen in this figure. In the Torres AGR nuclear power station, the summary design, which will be shown in the next figure, and it shows the many different design parameters that the plant follows, the different energy outputs, and the operating conditions that they may follow. It can be seen there that an AGR plant can operate using a coolant gas such as carbon dioxide and a moderator using graphite. And by following the parameters, it is said that the plant is able to gross out 660 megawatts of electrical energy and 1,620 megawatts of thermal energy, with an efficiency of 40.7% per plant. Now, the main data for the turbine plant are shown in the next figure. The turbine comprises of one single flow, 8-stage high-pressure turbine, one double flow 7-stage intermediate pressure turbine, and two double flow 5-stage low pressure turbines, from which the steam flows to a transverse underlying condenser. Now, for the operation concepts, here is Mr. Mendoza.
So for the operation concepts, first let's start off with the plant arrangement. In an AGR power station, the plant has two reactor units and one turbine house combined in a single complex with a central block for fuel handling, instrumentation and control. A so-called twin station. The reactor are served by one refueling machine operating with a common charge hall. The principal component of a typical AGR system are shown in this figure. So the reactor building is constructed with reinforced concrete, topped by the charge hall, superstructure of steel portal frames to a height of 74 meters above the level of the ground. In the AGR power plant, there are supply buildings housing diesel generators and switchgear. The reactor building together with the buildings previously mentioned are designed to be capable of seismic loads in case of earthquake disasters. The four buildings are located separate from the reactor buildings but close to one another to allow for maximum segregation. The reactor buildings also houses the high-level deaerators that reserve freshwater tanks and high-pressure steam feed for the piping network and for the power plant to function and create energy. It is important to note that the weight of the graphite moderator core weight loss is caused by progressive oxidation of the graphite moderator by carbon dioxide coolant. To inhibit this process, the loss of weight of the graphite moderator core, carbon monoxide and methane are used as coolant. However, addition to too much inhibitors leads to the decomposition of carbon on the boiler and fuel pins. So therefore, the AGR operators are faced with a balancing act to lower temperature to allow high methane levels allowing for longer core life but resulting in lower energy output, and to balance it with high temperatures and low methane levels, which allow for shorter core life but higher energy output. So now for the safety criteria. In any nuclear power plant, the different safety criteria play a vital role in different considerations in any nuclear power plant, such as design, construction, manufacture, and operation. The following guidelines should be strictly followed. No person shall receive doses of radiation under normal operation of a power station in excess of appropriate limits. The exposure of individuals to radiated materials must be kept as low as possible. And the collective dose equivalent to operators and general public as a result of the operation of a nuclear installation shall be kept as low as possible. So now let's proceed to the design of systems. This will be discussed by Angelo.
Thank you, David. So let's move on to the design of systems. So for the mechanical design, the reactor core, boilers, and gas circulators in a typical AGR system are housed in a single cavity, which is a pre-stressed concrete pressure vessel. The reactor moderator is a 16-sided stack of graphite bricks. The said moderator is designed to act as a moderator and to provide individual channels for fuel assemblies, control devices, and coolant flow. So the graphite used for the reactor moderator is covered by an upper neutron shield of graphite and steel bricks and mounted on a lower neutron shield of graphite bricks that rests on a steel plate. For radial shielding, steel rods are placed as two outer rings of graphite bricks. The shielding reduces radiation levels outside the core so that when the core is shut down and depressurized, access to the boiler is possible. There are two main effects of irradiation of the graphite moderator, and it is the first one is the dimensional change, and the other radiolytic oxidation by the carbon dioxide coolant. There will be also a significant decrease in the thermal conductivity as the temperature increases because of the relatively high pressure in the core. Steel envelope, also called as a gas baffle, enclose the core and the shield, the main function of which is to produce a downward flow of gas, coolant gas, through the pads in the graphite moderator to cool the graphite bricks to separate hot from the cold gas as seen in this figure. The gas baffle has three main sections: the dome, the cylinder, and the skirt. In the dome, there are many penetrations, for each of the fuel channels in the graphite moderator. The core and the radiation shields are supported on a structure called the diaphragm, which itself forms an integral part of gas baffle. Then, moving on to the nuclear design. The nuclear design is the reactor moderator is a 16-sided stack of graphite bricks, and the bricks are interconnected with graphite keys to give the moderator stability and to maintain the vertical channels on their correct pitch despite dimensional changes due to irradiation, pressure loads, and thermal stress. Not only it acts as a moderator but also provides the channels necessary for fuel assemblies, control rods, and coolant flow. Generally, the maximum permissible weight loss of graphite is about 5% over 30-year lifetime. Beyond this, the strength of the graphite begins to decrease significantly. The shielding is also important in that it reduces the radiation levels during the shutdown so that the boilers may be accessed. For control purposes, the control rods are inserted into the core, and under emergency conditions, beads and nitrogen may be injected between the fuel channels as means to absorb neutrons. Then, for the fuel assemblies, the fuel in AGRs consists of slightly enriched UO2 in the form of cylindrical pellets with a center hole. These are contained within stainless steel cladding tubes, each of which is about 900 millimeters long. A fuel element consists of 36 fuel pins surrounded by two concentric graphite sleeves. The fuel pins are supported by top and bottom grids, which are fixed to the outer graphite sleeve. The function of the double sleeve in the fuel element is to provide a static gas gap between inner and outer sleeve to reduce leakage of heat from the hot coolant to the graphite moderator. Then the fuel stringer assembly and its associated plug unit from a composite fuel assembly that is handled by the fueling machine and loaded into the reactor as one unit. Since it is important that the cladding exhibit good heat transfer properties, the cladding is provided with small transverse ribs on the outer surface and is compressed onto the pellets during manufacture to minimize the clearance gap between pellet and clad. So finally, it permits refueling both when the reactor is on and offload and for any pressure from atmospheric to form operating pressure by a fueling machine and handles a complete fuel assembly from the top of the vessel. And here is a figure of the fuel assemblies. Then for the thermal and hydraulic design, carbon dioxide gas is used to transfer the heat produced in the reactor to the boilers. The gas is pumped through the channels of the reactor at the high pressure by gas circulators. Its main flow paths are shown in this figure. The gas circulator pumps the coolant gas from the bottom of the boilers and into the space below the core. About half of this gas flows directly to the fuel channel's inlets, while the remainder, known as the re-entrant flow, passes through the annulus surrounding the core along the inner surface of the gas baffle to the top of the gas baffle. The baffle has to withstand full core pressure differential of 1.9 kg per centimeter squared, and its temperature is kept down to 325 degrees Celsius by insulation on the top side so that the mild steel can be used. And finally, the design for the reactor main coolant system, or the CO2 supply system. A carbon dioxide supply system is located on the site. Its purpose is to provide storage capacity for liquid carbon dioxide and supplies for gaseous carbon dioxide for each reactor, the refueling machine, and auxiliary plant facilities during normal operation and fault conditions. So the plant is also provided with a reactor coolant discharge system for controlled discharge of contaminated gas from the reactor and associated equipment it compromises. The reactor vessel blow down and purge system, one per reactor, the auxiliary blow down system, one per station, and the reactor vessel's safety relief valve system per two reactor. Thank you.